Welcome back, everyone. Ready for another deep dive. Today, we're taking a trip back to the world of geometry. Specifically, we're going to explore conic sections. You know those shapes you get by slicing a cone?
They're more than just shapes on a blackboard, though.
Yeah, I was thinking about that.
Yeah.
They always seem kind of abstract in school, but I have a feeling there's a lot more to them than I remember.
Absolutely. Understanding conic sections can unlock a whole new way of looking at the world. From the paths of planets to the designs of bridges, these shapes are hidden in plain sight everywhere.
Okay, now I'm really intrigued. Let's break it down. We're talking about parabolas, ellipses, and hyperbolas, right?
Right.
I remember the names from way back when, but honestly, the details are pretty fuzzy. Can we do a quick recap of what makes each one special?
Sure. Let's start with the parabola. Think about the path the ball takes when you throw it. That's a parabola.
Okay, yeah.
It has a single focus point, and every point on the parabola is the same distance from that focus as it is from a fixed line called the directrix.
All right, I'm picturing it. So what about the ellipse? What's its claim to fame?
An ellipse is like a stretched out circle. You know how you can draw a circle by putting a pin down, attaching a string to it, and tracing the path with a pencil?
Yeah.
Well, imagine you use 2 pins instead of 1. That's an ellipse. It has 2 focus points, and the sum of the distances from any point on the ellipse to those 2 foci is always the same.
Oh, that's a cool way to visualize it. So then what's the hyperbola all about?
The hyperbola, it's kind of the rebel of the group. Like the ellipse, it has 2 foci. But instead of a constant sum of distances, it's the difference of the distances from any point on the hyperbola to the foci that stays the same. And it's got these 2 branches that extend outwards forever, almost like it's trying to escape.
Okay, now I'm remembering why I found these shapes so fascinating. So where should we start our deep dive?
Let's start with parabolas and dive into something that might seem pretty basic, but it actually reveals a lot about their nature. The chord.
Chords.
Oh, wow.
Okay, those are just lines, segments connecting 2 points on a curve, right?
Yep, that's it. But every chord on a parabola has a specific equation that we can figure out. And things get even more interesting when we talk about a special type of chord called a focal chord.
Okay, a focal chord. Tell me more.
Well, it's just a chord that passes through the focus of the parabola.
So we have 2 points on the parabola, and the line segment connecting them has to go through that focus point.
Exactly. And here's the cool part. For any focal chord, if you take the parameters of the endpoints, let's call them TO and TOT, and multiply them together, you'll always get Mies of 1.
Whoa, really? So no matter where you put those 2 points on the parabola, as long as that line goes through the focus, that product is always Mies of 1.
Always. It's like this hidden rule that governs how those focal chords behave.
That's pretty wild. But is this just some mathematical quirk, or does it actually have some real-world implications?
It definitely does. Think about satellite dishes. Their shape is parabolic, and the receiver is located at the focus. This property of focal chords helps ensure that all those signals bouncing off the dish converge perfectly at the receiver, maximizing signal strength.
Wow, that's amazing. So this little geometric concept is helping us get crystal clear TV reception from space.
Now, let's look at another example that shows how beautifully these things work within parabolas. Imagine 2 chords going through the vertex of the parabola, and they're perpendicular to each other.
Okay, I'm picturing it. 2 chords, right angle, meeting at the very tip of the parabola.
Now, get this. No matter where you draw that first chord, the second chord will always intersect the parabola's axis at the same point. It's like there's this invisible anchor point on that axis that's controlling where those perpendicular chords go.
That's so strange. I mean, it feels counterintuitive that it would matter how you rotate that first chord. That second one would always hit the same spot on the axis.
It really highlights how much order and symmetry is hidden within these seemingly simple shapes. So to define a chord in simple words, we can say, a chord is a line segment joining any 2 points on the parabola.
Okay, I'm filing that away in my mental notes about parabolas. What other surprising things can these chords do?
Well, let's look at a chord where we know the point in the middle, not necessarily the endpoints. Can we still figure out its equation?
That's a good question. Feels like we need more information.
We actually can. We can use a cool trick. The equation of a chord with a given middle point, let's say x, x, s, e, o, for the parabola y equals 4x is given by t equals s. T represents the tangent equation at that midpoint, and S represents the value you get when you substitute x(s)0 into the parabola's equation, S.
So we're essentially using the tangent at that midpoint and the parabola's equation to define the chord itself.
Exactly.
That's clever. Can you give us an example to make it a little more concrete?
Sure thing. Let's say we have the parabola y widels 8x, and we know a chord has its midpoint at 2, 4. First, we need the tangent equation at 2 of 4, which is y4 equals 4x plus 2, simplifying to xy plus 2 equals 0. Then, plugging x2 and y equals 4 into our parabola equation, we get S0. 4 and 0, 8, 2, which equals 0. So the equation of our chord with the midpoint 2 out of 4 is simply xy plus 2 equals 0, the same as the tangent.
Well, that's neat. We found the chord's equation without even knowing its endpoints. Seems like tangents play a pretty big role in all of this.
Absolutely. Now think about this. What if a chord cuts through the parabola in such a way that it forms a right angle at the vertex?
Okay, I'm picturing it. The chord's endpoints on the parabola connected to the vertex make a 90-degree angle.
Right. Now, as that chord moves around the parabola, its midpoint actually traces a very specific path. Can you guess what shape that path would be?
Based on what we've seen so far, I'm going to guess another parabola.
Bingo. The path of the midpoint for all those right angle making chords is indeed another parabola. It's like a hidden parabola nestled within the original one. The simple definition of the chord with a given middle point is the equation of the chord of the parabola y-y-axis, whose midpoint is xy, is y-a-x plus xx.
Whoa, that's incredible. Parabolas within parabolas. Does this have any practical use, or is it just a really cool geometric fact?
It actually has some real-world applications. When engineers are designing things like bridges or arches, which often have parabolic shapes, understanding how these chords and midpoints behave helps them analyze how forces will be distributed. This knowledge helps ensure those structures are stable and safe.
It's amazing how much depth there is to these seemingly simple shapes. We've talked about chords and their different properties. What other fascinating concepts should we explore with parabolas?
Let's dive into another important pair, the subtangent and subnormal.
Okay, I have to admit, those terms are not ringing any bells. Can you enlighten me?
Of course. Imagine you have a point on a parabola, we'll call it point P, and you draw a tangent line at that point. Now, from point P, draw a line straight down, perpendicular to the parabola's axis. That's your normal. The subtangent is the segment of the axis between the parabola's vertex and the point where the tangent line crosses the axis. The subnormal is the segment of the axis between where the normal hits the axis and the point directly below P on the axis.
So we've basically created a right triangle with the tangent, the normal, and a portion of the axis.
Precisely. And just like with the chords, there are formulas for calculating the lengths of both the subtangent and the subnormal. At a point at the parabola 2x, on the parabola 4x, the subtangent's length is simply 2x, which is double the x-coordinate of that point. The subnormal's length, however, is always fixed at 2a no matter where you are on the parabola.
So the subtangent's length changes depending on the point.
Yeah.
But the subnormal is always constant. What does that tell us about parabolas?
It speaks to the inherent balance and order within these shapes, and these lengths have practical implications too. For instance, the subnormal's constant length is a crucial factor in designing those parabolic mirrors used in telescopes. It helps ensure that light rays converge precisely at the focus, which is essential for getting clear images.
Wow, another real-world connection. Parabolas seem to be full of hidden depths.
They truly are. So, in simple terms, the subtangent is the projection of the segment of the tangent between the point of contact and the point where the tangent meets the x-axis on the x-axis, and the subnormal is the projection of the segment of the normal between the point of contact and the point where the normal meets the x-axis on the x-axis.
Okay, my parabola knowledge is definitely expanding. We've covered chords, subtangents, subnormals. What's next on our parabola adventure?
Let's move on to another key player, the tangent.
Okay, tangents. I remember those as lines that just graze a curve at a single point.
That's right. And tangents to parabolas have some unique properties that make them worth exploring. There are actually a few different ways we can express their equations.
Sounds good. I'm ready to take notes.
First up is the point form. If we know a point on the parabola, x 0, and the parabola's equation is euro at 1 old equals 4x, the equation of the tangent at that point is euro equals 2ax plus m. Then we have the slope form. If we know the slope of the tangent, let's call it m, the equation is y equals m plus 1m. And lastly, there's the parametric form. For this one, the tangent at the point at green here is at equals x plus at work.
So we've got a point form, a slope form, and a parametric form. That's a lot of options. Why do we need so many different forms?
Each form is handy in different situations. If you know a specific point on the parabola, the point form is the easiest to use. But if you know the direction of the tangent, meaning its slope, then the slope form is more convenient. And if you're working with the parabola in terms of a parameter t, the parametric form is your go-to.
Okay, that makes sense. So what kinds of cool things can we learn about parabolas by studying their tangents?
Well, there's this fascinating connection between tangents and those focal chords we were talking about earlier. Remember, a focal chord has to pass through the focus of the parabola.
Yep, and we learned that the product of its endpoints parameters is always Meckel 1.
Right. Now imagine drawing a tangent to the parabola at one of the endpoints of a focal chord. That tangent line will always be parallel to the line connecting the parabola's vertex to the other endpoint of that focal chord.
Wow, that's like they're perfectly coordinated. So to simply define a tangent to parabola, we can say a straight line which touches the parabola at only one point is called a tangent to the parabola at that point. The point is called the point of contact.
Exactly. And this relationship holds true no matter how you manipulate the parabola. It's a testament to the elegance and interconnectedness of these geometric principles.
I'm really starting to see those connections everywhere. Okay, we've explored tangents and their equations. What else is there to learn about them?
Let's imagine you draw two tangents to a parabola, both starting from a point outside the curve. Now connect the points where those tangents actually touch the parabola. That line segment you just drew, that's called the chord of contact.
Oh, okay, so it's like those two tangents are leaving their mark on the parabola with that chord. Is there a way to find its equation?
There is. For a parabola with the equation 1g is equals 4x, and tangents coming from a point euro, the equation of that chord of contact is your x is 2ax plus x0. Does that ring a bell?
Hold on. That looks familiar. Isn't that the same equation we use for the point form of a tangent?
You got it. It's the exact same equation. It's
Yeah.
pretty amazing how connected these concepts are.
That is pretty neat. Okay, so now what if we wanted to find the equation for the pair of tangents, not just the chord of contact?
Good question. We can do that too. The equation for the pair of tangents from the point x0y to the parabola y equals 4x is s0 is equals t1 better. Here, s is just the parabola's equation itself. Y 4x equals 0. S is what you get when you plug x0 and euro into the parabola's equation, so you are 4x0. And t is the equation of the tangent at x0, which we know is y ru 2ax plus x0.
Okay, that's a little more complex, but it seems like we're essentially combining the equations for the parabola and the tangent to get the equation for the pair of tangents. To define chord of contact in simple words, we can say the chord joining the points of contact of the tangents to a parabola 1 when equals 4x drawn from a given point is called the chord of contact of the tangents to the parabola from that point.
You nailed it. The beauty of math is how it can express these relationships so elegantly. Now let's try a visual example for the chord of contact.
Visuals always help me.
Imagine you have a circle nestled perfectly between two tangents to a parabola. The circle touches the parabola at the exact spots where the tangents graze it. The segment of the tangents, the part between where they cross and where they touch the parabola, that's the diameter of the circle.
Okay, I'm picturing it. Two tangents, circle snuggled in between, touching the parabola.
Now here's the cool part. No matter where you draw those initial tangents, that circle you drew, it will always go through the parabola's focus.
Whoa, really? It's like the focus has a magnetic pull on that circle. Why is that?
It's just another example of these hidden relationships within conic sections. And this property is really useful for things like geometric proofs and design. It gives you this fixed connection you can rely on.
Okay, that's another one for my amazing parabola facts list.
Now, we've talked a lot about tangents. Let's shift gears and talk about their counterpart, the normal.
Normals. Right, they're perpendicular to the tangents, like two opposite forces working together.
Exactly. And just like with tangents, there are different ways to write the equation of a normal to a parabola. We have the point form. At a point x, a, u, I, the equation of the normal is y, a, u, a, e, x, a. Then we have the slope form. If aim is the slope of the normal, the equation is y equals mx2 a.
Okay, so with these equations, we can pinpoint the normal at any point on the parabola. But where do normals come into play in the real world?
Normals are really important in physics, especially when we're studying motion and forces. Think about a baseball flying through the air. Its path is a parabola, right?
Yep.
Well, the normal at any point along that parabola tells us the direction of the force acting on the baseball at that exact moment.
Whoa, that's awesome. So we're using geometry to understand the unseen forces shaping a baseball's flight.
Now, here's an example that shows just how interesting normals can be. Imagine you have two normals drawn to a parabola from the same point outside the curve.
Okay, so two lines, both perpendicular to the parabola, both starting from the same point. Got it.
Let's say these normals make angles in f with the parabola's axis. If you multiply the tangents of those angles, tan bup, and it equals 2, then something interesting happens. The point from which you drew those normals will always lie on a specific curve.
Wow, so the position of that point is determined by the angles of those normals.
Yeah.
That's really cool. What's that special curve called?
It's called the locus of that point.
Yeah.
In this case, the locus of the point will be another parabola. To define normal to parabola in simple terms, we can say the normal at any point on a parabola is the straight line which passes through that point and is perpendicular to the tangent at the point.
Parabolas creating more parabolas. My mind is bending a little bit. So how is this concept used practically?
This idea is used in curve fitting, which is all about finding the best curve to represent a set of data points. Imagine you're a scientist analyzing data from an experiment. Understanding the relationships between normals and their loci can help you find the most accurate parabolic curve to fit that data, leading to more reliable conclusions.
Okay, that's really neat. It's like these geometric relationships give us tools to make sense of the world around us. I'm really starting to see how much depth there is to parabolas.
And we've only just scratched the surface. Are you ready to move on to another fascinating conic section, the ellipse?
Absolutely. Bring on the ellipses.
Ellipses are super interesting because they're all about distances. Imagine you have two fixed points called foci. Now, picture a point moving around in such a way that the sum of its distances from those two foci always stays the same. The path that moving point traces, that's an ellipse.
So it's all about maintaining a constant total distance from those two focus points. That's a pretty cool way to define a shape. It reminds me of those drawing tools where you have a string attached to two pins.
Exactly. Now, like our other conic sections, ellipses can be represented by an equation. The standard equation, centered at the origin, is x or b a plus y OA. Here, a and b are the semi-major and semi-minor axes, respectively. Basically, a is the distance from the center of the ellipse to a vertex along the long axis, and b is the distance from the center to a vertex along the shorter axis.
So A and B control how wide and how tall the ellipse is. Where do the foci we were talking about fit into this equation?
The foci are located at A0, where he represents the ellipse's eccentricity.
Eccentricity. Now, there's a word I've heard before.
Yeah, we use it to describe people who are a little different, right? But in math, eccentricity measures how stretched out an ellipse is. It's calculated as EFO1BA.
So a perfectly round circle would have an eccentricity of 0.
That's right.
And a super elongated ellipse, one that's almost flat, would have an eccentricity close to 1. It's like a measure of how oval-shaped it is.
Perfect analogy. Now, ellipses have a bunch of important parts that define their shape and characteristics. We've already talked about the major axis, the longer axis, which has a length of 2a. Then there's the minor axis, the shorter one, with a length of 2b.
Right, so those give us the ellipse's overall dimensions. What else is there?
Well, we have the vertices, which are the points where the ellipse crosses the major axis. And then there's the latus rectum. It's a chord that goes through a focus and is perpendicular to the major axis. Its length is given by 2BYO.
Okay, so these are like landmarks on the ellipse marking important spots.
Exactly. And then we have the directrices. Each ellipse has two directrices. These are lines that run parallel to the minor axis, and they're located a distance of a from the center.
Wow, it's like this whole intricate web of lines and points that work together to create the ellipse. What's the role of those directrices?
They play a key part in the geometric definition of an ellipse. For any point on the ellipse, if you take the ratio of its distance from a focus to its distance from the corresponding directrix, it will always be equal to the eccentricity.
That's a pretty neat property. It's like this constant ratio that's governing how the points on the ellipse relate to the foci and the directrices. To define the ellipse in simple words, we can say, an ellipse is the set of all points in a plane, the sum of whose distances from two fixed points in the plane is a constant.
You got it. It's all about balance and order. Now, let's try an example to see how all of these pieces fit together. Imagine we know that the foci of an ellipse are at 5, 0, and the length of its latus rectum is 185. Can we figure out the equation for this ellipse?
That sounds like a fun challenge. Where do we even begin?
Well, remember, the foci are at 0. Since the foci are at 5, 0, we know that AAB is 5. We also know that the length of the latus rectum is 2BA, and we're given that it's 185. So we've got two equations and two unknowns, A and B.
It's like a detective puzzle.
Exactly. If we solve those two equations together, we can find the values A and B. Then we can plug those values into the standard equation of an ellipse, and boom, we've got our equation.
I love how it all comes together. It's really satisfying seeing how we can use these concepts to uncover the secrets of the ellipse.
Now that we've got a grasp of the equation and the different parts of an ellipse, let's talk about location. How can we tell if a point lies inside, outside, or on the ellipse?
Ooh, that's a good question. It's like defining the ellipse's boundaries. How do we figure that out?
Let's say we have an ellipse with the equation xa plus yb 611, and we want to know where a point x sub ui sits in relation to this ellipse. All we have to do is substitute those coordinates into the left-hand side of the equation.
So just plug in the point's x-coordinate for x and the u-coordinate for y, right?
Yep. Then we just look at the result. If the result is less than 1, then the point is inside the ellipse. If it's greater than 1, it's outside. And if it equals exactly 1, the point is right on the ellipse's curve.
That's such a simple way to figure it out. It's like a test to see if a point made it into the ellipse's club.
And this concept has tons of real-world applications. Think about astronomy. Let's say astronomers are tracking the path of a comet, which often follows an elliptical path. By knowing the equation of that comet's orbit, they can use this method to figure out if the comet will come within a certain distance of Earth.
Wow, so we're using math to predict cosmic events.
It all comes down to understanding the relationships between points, distances, and curves.
We've covered a lot of ground with ellipses. We've defined them, talked about their equation, their key components, and even how to tell where points lie in relation to them. What's next on our elliptical adventure?
Remember those special lines we talked about with parabolas, tangents, and normals? They're just as important when we're talking about ellipses.
Okay, so tangents and normals, round 2.
Yeah.
What do they look like with ellipses?
Just like with parabolas, there are different forms we can use to express the equations of tangents to ellipses. The point form equation of the tangent to the ellipse plus ybb non at a point xeu is xaeo plus yo1 plus xianus 1.
That looks a bit similar to the tangent equation for parabolas. Do the slope and parametric forms look similar too?
They do, but with some twists to account for the ellipse's unique geometry. The slope form, where m is the slope of the tangent, is y equals mx plus mex 1. And the parametric form at a point x base sin is x base te plus a sin x equals 1.
Okay, so we've got a whole toolbox of tangent equations to use depending on the situation. What about normals? How do they differ from what we saw with parabolas?
The equation of the normal at the point x we on the ellipse plus y piece would is x scores 1 is x p stay plus x y if.
Yeah, it's interesting to see how the equations change depending on which conic section we're working with. What are some interesting things we can learn about ellipses through these lines?
One really cool concept is something called the director circle of an ellipse. Imagine drawing tangents to an ellipse from a point outside the curve, and those tangents happen to intersect at a perfect right angle. The director circle is the set of all those points from which you can draw those perpendicular tangents.
So it's like a special circle that contains all the points where we get those perfect right-angle tangents.
That's a cool visual. What's the equation for this director circle?
The equation of the director circle for the ellipse, xxo applies 1, is xob plus a plus 8 plus b.
So the ellipse's semi-major and semi-minor axes determine the size of its director circle. It's like the ellipse is controlling the boundaries of its own special circle.
Exactly. And here's where things get even cooler. If you draw tangents to an ellipse from any point on its director circle, those tangents will intersect the ellipse at points where the normals to the ellipse at those points are perpendicular to each other.
Whoa, that's a lot of geometric action. It's like the tangents, normals, and director circle are all working together in this beautiful, synchronized way. To define tangent to an ellipse, in simple terms, we can say, the tangent at any point on an ellipse is the straight line, which touches the ellipse at only one point. It's a perfect example of how interconnected mathematical concepts can be. Now, remember those chord concepts we talked about with parabolas, like chords of contact, pairs of tangents, and chords with a given midpoint? Guess what? They apply to ellipses too.
Oh, so we're back to chords. How do they work with ellipses?
The equation of the chord of contact for an ellipse, x ambiential plus y b1, with tangents drawn from a point, x arrow contact plus y b1 plus eo o1. Does that look familiar?
It's the same as the equation for the tangent at a point on the ellipse. It's interesting how this connection between tangents and chords of contact seems to be a recurring theme.
That's a great observation. There are a lot of these relationships that hold true across different shapes. It points to a deeper underlying structure in geometry. And just like with parabolas, the equation for the pair of tangents from a point x euro to the ellipse is ss euro equals t1, where s represents the ellipsis equation, s is the value of s when we substitute x euro as y, and t is the tangent equation at x euro euro. Similarly, the equation for the chord with the even midpoint x euro or on the ellipse is t equals s euro.
So those chord equations are like universal tools for understanding conic sections. So to define normal to an ellipse, in simple words we can say, the normal at any point on an ellipse is the straight line, which passes through that point and is perpendicular to the tangent at the point.
Exactly. Recognizing these patterns and connections is a big part of understanding mathematics. Now, before we move on to hyperbolas, let's look at one more cool property of ellipses related to normals.
Okay, I'm all ears.
Picture this. You have a normal line cutting through an ellipse. It intersects both the major and minor axes.
Right, I can see it.
Let's call the point where the normal hits the major axis G and the point where it hits the minor axis G. Now connect those 2 points, G and G, with the line segment. If we find the midpoint of that segment, something interesting happens. As the normal moves around the ellipse, that midpoint will trace out another smaller ellipse.
Whoa, it's like ellipses within ellipses. These shapes are full of surprises. What's the significance of this?
It just shows how interconnected everything is in geometry. This property is important in understanding how light behaves as it passes through things like elliptical lenses or reflectors.
Okay, my mind is officially blown. Ellipses are so much more complex than I ever realized. We've talked about their definition, their equation, all the different parts, tangents, normals, chords. It's a lot to take in.
And we're just getting started. There's a whole universe of intricate details and relationships to discover within conic sections. But now, are you ready to tackle our final conic section? The hyperbola.
Absolutely. Bring on the hyperbolas.
Hyperbolas are kind of the dramatic ones of the group, full of intriguing properties. They're defined as the set of all points in a plane, where the difference of the distances from 2 fixed points, the foci, is a constant.
Okay, so instead of a constant sum of distances, like with ellipses, we're looking at a constant difference. It sounds like ellipses and hyperbolas are like two sides of the same coin.
You're right to notice that connection. They're often seen as complementary shapes.
I love that idea.
Yeah.
What about the equation of a hyperbola? Does it look anything like the ellipse's equation?
It does, but with one key difference. The standard equation for a hyperbola centered at the origin is xAILT-ROBFBO 12 EBOS 1. That minus sign is what sets it apart from the ellipse's equation.
So it seems like that subtraction is what gives the hyperbola those two outward curving branches, making it look so different.
Exactly. And just like the ellipse, hyperbolas have some important parts that define them. We have the transverse axis, which connects the 2 vertices of the hyperbola. Its length is 2a.
So the transverse axis is like the backbone of the hyperbola. What about the other axis?
We have the conjugate axis. It's perpendicular to the transverse axis and has a length of 2b. It's important to remember that, unlike with ellipses, where the major axis is always longer, the transverse axis in a hyperbola can be shorter than, longer than, or even equal in length to the conjugate axis.
Interesting. So hyperbolas have a bit more freedom in their proportions.
Mm-hmm.
What about the foci? Where are they located in a hyperbola?
Just like with ellipses, they're located at G0, where he is the eccentricity.
So eccentricity for a hyperbola still measures how stretched out it is.
Yep. But the formula is slightly different. For a hyperbola, it's E1 plus BAA. Notice it's a plus sign this time.
So the eccentricity of a hyperbola is always greater than 1, which makes sense given those outward curving branches. It's like a measure of how bold it is.
Precisely. Now let's talk about another key feature of hyperbolas. They're asymptotes.
Asymptotes, right? Those are lines that a curve approaches but never actually touches. Like it's always getting closer but never quite reaching them.
That's the idea. Hyperbolas have 2 asymptotes that intersect right at the hyperbola's center. They act like guiding lines that define the shape and direction of those branches as they extend out forever.
It's like a cosmic dance of approach and avoidance.
I love that description. And we can easily find the equations of those asymptotes. For the hyperbola asymptotes, the equations of its asymptotes are we by make x.
So the slope of the asymptotes depends on the ratio of the conjugate axis to the transverse axis. Makes sense, since the asymptotes guide the direction of those branches.
Exactly. Hyperbolas also have a latus rectum, just like parabolas and ellipses. It's a chord passing through a focus and perpendicular to the transverse axis, with a length of 2b Bray.
It's cool how certain elements, like the latus rectum, are present across all these different shapes.
That's a key insight in geometry. Recognizing those common threads helps us see the bigger picture. So to define hyperbola in simple terms, we can say, a hyperbola is the set of all points in a plane, the difference of whose distances from 2 fixed points in the plane is a constant.
Okay, this is fascinating. What else can we discover about hyperbolas?
Well, for every hyperbola, there's a special counterpart called its conjugate hyperbola.
Conjugate hyperbola. What's so special about that?
Think of it as a mirror image of the original hyperbola flipped along its asymptotes. They share the same center and the same asymptotes, but their transverse and conjugate axes are swapped.
Oh, I see. So if the original hyperbola opens horizontally along the x-axis, its conjugate would open vertically along the y-axis. They're like perfect complements to each other.
Exactly. The equation of the conjugate hyperbola for xx1 is natural x1. Notice how the signs are flipped.
That's a cool detail. What's the significance of the conjugate hyperbola?
It helps us understand the symmetry and relationships between hyperbolas. Did you know that if you take the two foci of a hyperbola and the two foci of its conjugate, they always form the corners of a rectangle?
Wow, that's amazing. It's like they're intertwined, their properties linked together.
It's another example of the beautiful order within conic sections. Now, just like with parabolas and ellipses, we can explore tangents and normals in the context of hyperbolas.
Okay, I'm ready to see how those familiar lines work with hyperbolas.
The point form equation of the tangent to the hyperbola xag1 at a point x0 is xaaa equals 1.
That looks pretty similar to the tangent equation for ellipses, but with a minus sign.
You're right. And we also have the slope form and the parametric form for tangents to hyperbolas. The slope form, where m is the slope, is yamx may amx aaoa. The parametric form at a point, x0, is xaaa equals 1.
So we've got all our tangent equations covered. What about normals?
The equation of the normal at a point on the hyperbola x081 is xac xaoas plus ao plus a.
Okay, so we've got our formulas for tangents and normals. Are there any interesting properties or relationships we can find when we use these lines with hyperbolas?
Definitely. There's a really cool connection between the asymptotes of a hyperbola and its tangents. Imagine a point on a hyperbola and the tangent line at that point. If you extend that tangent line so it crosses both of the hyperbola's asymptotes, the segment of the tangent line between those two crossings will always be perfectly divided in half by the point of contact on the hyperbola.
Wait, so the hyperbola acts like a midpoint, perfectly splitting that tangent segment. That's really neat.
It is, and it highlights how the asymptotes influence the hyperbola's tangents. This property is really helpful in understanding the geometry of conic sections. So to define tangent to the hyperbola in simple terms, we can say a straight line which touches the hyperbola at only one point is called a tangent to the hyperbola at that point. The point is called the point of contact.
I'm seeing more and more how conic sections are all about these fascinating relationships between curves, lines, and points.
Exactly. Now, just like with parabolas and ellipses, those familiar chord concepts we talked about, chords of contact, pairs of tangents, and chords with a given midpoint apply to hyperbolas too. They follow the same patterns we've already seen.
It's fascinating how these chord equations seem to be a universal tool for understanding conic sections. So to define normal to the hyperbola, in simple terms, we can say the normal at any point on a hyperbola is the straight line which passes through that point and is perpendicular to the tangent at the point.
You got it. Now, there's a special kind of hyperbola where these relationships become even more interesting, the rectangular hyperbola.
Rectangular hyperbola, what makes it so special?
A rectangular hyperbola, also known as an equilateral hyperbola, is one where the asymptotes are perpendicular to each other.
So it's like a perfectly balanced hyperbola with its branches spreading out equally in all directions.
It's a great way to visualize it. Its equation is also quite simple. xy is c-force, where cc is a constant.
Wow, that's a lot simpler than the standard hyperbola equation. What else is special about rectangular hyperbolas?
Well, their eccentricity is always dread too. And the length of their lattice rectum is equal to the length of their transverse axis, which is also equal to the length of their conjugate axis. They're all equal to 2c.
So rectangular hyperbolas are all about equality and balance.
Precisely.
Yeah.
Here's another intriguing property. Any tangent to a rectangular hyperbola forms a triangle with the hyperbola's asymptotes, and that triangle always has a constant area.
It's like the rectangular hyperbola is imposing its order and balance onto the tangents as well.
Exactly. And of course, rectangular hyperbolas have equations for their tangents and normals too.
All right, let's see how those equations look in the simplified world of the rectangular hyperbola.
The equation of the tangent to the rectangular hyperbola xi equals c chord at a point, ct, is x plus yt or equals 2ct.
That's a lot shorter than the tangent equation for a standard hyperbola.
It is. And the equation for the normal at the same point is x2y equals c21.
Even the normal equation has a certain simplicity to it. It's amazing how rectangular hyperbolas manage to be both simple and fascinating. So to define a rectangular hyperbola in simple terms, we can say A hyperbola whose asymptotes are perpendicular to each other is called a rectangular hyperbola.
They're a beautiful demonstration of the power of symmetry and balance.
This has been an incredible journey through the world of conic sections. We've explored parabolas, ellipses, and hyperbolas, delving into their definitions, equations, and so many fascinating properties. It's amazing to think about all the hidden depths and complexities within these seemingly simple curves.
And the best part is, we've only just begun to explore. There's a whole universe of intricate details and relationships to discover.
I'm definitely feeling inspired to keep learning more. Do you have any final thoughts or parting words for our listeners as they continue exploring the world of conic sections?
It's incredible to realize that these conic sections aren't just abstract math, they're all around us.
I know. That's been one of the biggest takeaways for me. We've seen how parabolas are behind the designs of telescopes and the way things fly through the air.
Exactly.
We've seen how ellipses dictate the orbits of planets. And hyperbolas, too. They pop up in physics and economics, even.
They really are everywhere. So keep your eyes peeled. You'll start seeing them in the arches of bridges and buildings, in the way light and shadows interact, even the ripples in a pond after you throw a stone.
I already feel like I'm seeing the world differently now. It's like a whole hidden layer of geometry has been revealed. Before we finish up, do you have any last thoughts to leave us with? A question, maybe, to keep our listeners thinking.
Here's something to ponder. We've spent all this time looking at these shapes individually, but what happens when they start interacting?
Oh, like when they intersect or overlap.
Exactly. Think about a parabola and an ellipse crossing paths, or a hyperbola slicing through a circle.
That opens up a whole new level of complexity.
It does. What kinds of new geometric insights can we uncover by looking at how conic sections combine and interact? And what practical applications might those insights have?
Those are fantastic questions. I feel like we're just scratching the surface of what's possible with conic sections.
That's the beauty of learning. There's always more to discover. Keep asking questions, keep exploring, and keep diving deep into the world around you.
That's great advice. Thanks so much for being our guide on this incredible deep dive into conic sections.
It was my pleasure.
And to all our listeners out there, until next time, keep those brains buzzing.